All right, good morning, everyone. So today we'll continue with SN1 and we'll talk a little bit about E1. I'll give you a short review on, on all of this and, well, not really a review. I want to give you a different perspective on this at the end of class that might be useful. And then no class on Friday, obviously. Monday will be a review of the entire chapter. So we'll try to sort of bring everything together in a way that's helpful for you. Next Wednesday, we'll have class. That'll be new material, but it won't be on the exam. And then Friday, we'll distribute the exam, and we'll do the same thing we did for the second exam. You'll have 12 hours to complete it. I know some of you have schedules on Friday. I'm going to try and find a more systematic way to accommodate. I'll have an update for you on Monday about that. Okay. So essentially today's lecture is going to be the last bit of new material for the third hourly exam. And so what I want to do is drill down a little bit more on the SN1 pathway. And so oops. Okay. And so generally, SN1 is going to be most common for tertiary substrates. You'll sometimes see secondary, but generally it's going to be tertiary. It's almost never, ever going to be primary or methyl. And so if you see a primary or methyl substrate and you're trying to think, is this going to react by SN1 or SN2, you don't need to think any further, okay? Those will not react and by an SN1 pathway. And the reason, of course, is that you go through this carbocation intermediate. It's very high energy when you have a methyl or a primary substrate. So okay, so again, like I sort of warned you in the beginning of this chapter, secondary substrates are always the murky ones. And when you're asking the question, are they going to do an SN1 or SN2, you need to carefully look at the other reaction conditions. Okay, so we covered this in last class, but I'll draw the general mechanism again. So the SN1 is a two-step process, and it's most commonly going to be carried out in polar protic solvents, where the solvent is also your nucleophile. Okay, so we can use methanol as a case. Can you guys hear me okay? They're cutting the grass outside. It sounds like there's a lot of noise in my office. Okay, thanks. Okay, so the solvent will typically also behave as a nucleophile, and there's a specific term for that, which is called a solvolysis. And so it's, you're basically reacting the substrate with solvent. Okay, and so the first step is the unimolecular ionization of the substrate to generate a carbocation intermediate. Plus, in this case, I minus. Okay. And in the second step, that carbocation is going to be trapped by solvent, in this case, methanol. Okay. And the methanol, there's no base around. The methanol adds in its neutral form. And the immediate product, when you trap that carbocation by the solvent, is going to be the protonated product. Okay. And then the final step is a proton transfer. So what we typically do is invoke another solvent molecule coming in and removing that proton. And so what you wind up with is the neutral product plus protonated solvent plus the leaving group, in this case, I minus. Okay. So just to iterate, there's, SN2 was one step reaction, right? In the SN1, there's actually three. So the first step is ionization. The second step is, we can say, addition. And then the third step is proton transfer. So three discrete transformations in that reaction. Okay. So what types of conditions favor SN1? And we'll do the same thing we did for SN2, substrate, nucleophile, solvent, leaving group. But we're going to go through it more quickly just because we've already, sort of explained, what makes a good leaving group, what makes a good nucleophile, et cetera. So So conditions favoring SN1, as far as the substrate is concerned, tertiary, some secondary, and then never primary or methyl. And this is a consequence of that carbocation intermediate. We know that primary methyl cations, very high in energy, secondary sort of in the middle, tertiary are the most stable among the alkyl cations. So for the nucleophile, the most important thing is that it's going to be non-basic. And what that typically means is that it's going to be neutral, okay? Okay. And the reason for this is that because the first step in the SN1 reaction is this unimolecular ionization, I'm just breaking a bond. I get no bond forming. There's no bond forming in that first step, right? And so that step costs me exactly what it costs to break that bond. What that means is that you're going to have a high activation energy, which translates to a slow reaction. And so you could imagine, let's say the T1 half for ionization of your substrate under a set of conditions is 10 hours. um, at 10 hours you're going to have 50% ionization, but if you have a strong base in there, you're going to get elimination, which is going to be competitive. Those are typically much faster reactions, T1 half, maybe 1 hour. And so essentially, because that ionization is very slow, it opens up a window for other reactions to emerge. And so to suppress those, we really want to use a nucleophile that's going to be non-basic. It won't do any sort of elimination. Okay, so okay, and then the solvent. Um, Essentially, you're always going to see polar protic solvents. Okay, I'll come back to this in a second. But the key point is that you generate in the first step an ion pair. That ion pair is going to be most stable in a polar solvent that can hydrogen bond to the anionic leaving group. Okay. And so that, we're almost always going to be running solvolysis reactions, and it'll be methanol or ethanol as your solvent. Okay. And then the final thing is the leaving group. This doesn't differ too much from the SN2. You need a good leaving group. You need a leaving group that will readily accommodate a negative charge. And typically that's going to mean a very, very low pKa. Okay. So the pKa of the conjugate acid of the leaving group, just like the SN2, should be less than 0. So there's nothing that you need to really sort of rethink there. Okay. I want to say two things about this carbocation. So there are two important factors that arise because we go through this carbocation intermediate. And the first, I touched on this at the end of class on Monday, but let me go through it again, which is that because the carbocation is planar, any stereochemical information that may be lost, may be present in the starting material is going to be lost. And so Okay. And so, for example, if I take a chiral tertiary alkyl halide, and we're going to say that I've got a single enantiomer of the starting material. And remember, I'm writing chiral single enantiomer there just to like emphasize the point. But if I just draw that compound as a single enantiomer, the implication is that it's a single enantiomer. If I put the plus minus underneath, that tells me that it's racemic, okay? So if you take this substrate, such as this one, heat it up in methanol, you'll form a carbocation. Okay, and of course that carbocation is flat, and so what I've done is I've taken that chirality in the starting material and abolished it in the carbocation. You go from a molecule that lacks a planar point of symmetry to one that has a plane of symmetry. And so what that means is that my methanol has an equal probability of coming in at the top, call that path A, or at the bottom, call that path B. Okay. And so if I do the addition and then lose a proton, you get to two products. And so we would have this structure here, and this derives from path A, and then the alternate structure deriving from path B. Okay. And if you can't see it, you want to, I would encourage you to convince yourself that these are in fact enantiomers of each other, okay? And so the take-home message is that in an SN1 pathway, enantio-enriched starting material gets transformed to racemic product, okay? Okay. And so this is often diagnostic for an SN1. So for example, you've got a substrate that you made in lab and you want to do a substitution on it. And you want to know if that substitution is proceeding via an SN1 or an SN2 pathway. Obviously, you can look at the reaction parameters and the structure of the substrate and make a judgment call. But we like to get experimental data. And so one of the things that we can look at is the stereochemical outcome of the reaction. And so if I have a single enantiomer of starting material and it goes to racemic product, that's diagnostic of an SN1 pathway. If I have a single enantiomer of starting material and it goes to an enantio-enriched product, and in particular, the EE of the product is the same as the starting material, that's diagnostic of an SN2 pathway, okay? There's a small caveat here, which I'll touch on at the end of lecture, which is that you don't always get full racemization, okay? And if you just bear with me, I'll explain this in more detail. It's a minor point. It's not one you guys really need to worry about, but it's worth mentioning, and I'll explain it in detail when we get to the end of lecture. Okay. All right. The second consequence of this carbocation intermediate is what? Does anyone want to venture a guess? You know, what do carbocations do that we have to worry about?
Rearrangement.
Yeah, exactly. Yep. So just like with acid catalyzed addition of alkenes, we make a carbocation, SN1, you make a carbocation, it's subject to the same, the same issues. So watch for rearrangements. Okay. And so, for example, if you take this substrate and heat it up in methanol, right? You can generate a carbocation. And again, so this is a secondary substrate. It's one of those borderline cases. It's probably worth mentioning why this would go by an SN1 pathway. So first of all, it's secondary, so it's possible. Second of all, I've got a weak non-basic nucleophile in methanol. So methanol is not going to behave as a base and eliminate HI by an E2 type of pathway. And then the third thing is that the reacting center, if we call that again alpha, call this beta, it's beta 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 tri-substituted, and so a SN2 type of displacement would be very difficult. This is, if you get rid of that terminal methyl group on the right, that's neopentyl iodide. This is worse than that because I now have that additional methyl. So this is going to be a decent SN1 substrate. It'll ionize, make the carbocation, and then you're kind of off to the races. And so you can trap that. Or you can do a 1-2 shift. And that would generate a more stable secondary carbocation, or sorry, tertiary carbocation. And then if that gets trapped, you wind up with the isomer. And in fact, this rearranged product, as you might expect, is the major. The unrearranged is the minor product, okay? So those are the two things that you have to keep in mind. Loss of stereochemistry, and because we make a carbocation, watch out for rearrangements, okay? I want to say a little bit about solvent effects. And so you don't need to worry too much about this. And it's not really this isn't like a simplification for the class. Most of the time these reactions are run in polar protic solvents where the solvent behaves both as nucleophile and solvent. And so we can think about what the effects are or why that's important to promote the SN1 reaction. So Okay, so it's generally only going to occur in a polar protic solvent. And so if you think about, model reaction, tert butyl iodide, heating that up in methanol. Okay, ionization, trapping by methanol, proton transfer. What we want to do is really just focus on the first two steps here. And if we put that on a reaction energy diagram, okay, we can say here's our tert butyl iodide plus your methanol, right? And it's got some energy. I'm going to ionize up. That's the rate determining step. And so I have the tert butyl cation plus I minus, right? Plus methanol. And then you get trapped and you go down to that protonated product, okay? And so the key thing is actually, if you look a little more closely at what's happening with the I minus, it's not I minus just sitting in solution, right? It's actually hydrogen bound. So right. And so it is that hydrogen bonding that promotes this reaction. Okay. I am paying for breaking that CI bond. And part of the way that I can compensate is by making hydrogen bonds. And so you can effectively think about those hydrogen bonds as being subtracted from the bond enthalpy of the CI bond and reducing the delta G between these intermediates and the starting material, okay? And if you were to change this reaction and say, run it in acetone, which can't hydrogen bond, a very polar solvent, but it can't hydrogen bond with, say, like an equivalent of methanol. So we'd be starting with the same compounds, but let me use red here. There's a good color for this, but you're going up much higher. And the energy of those intermediates is going to be much higher. And so the activation energy then is going to be much higher. Remember that this first step is an endothermic process, right? I'm breaking a bond. It costs me bond enthalpy. The carbocation is going to look more like, or sorry, the transition state is going to look more like the species that's closest in energy, in this case, the carbocation plus I minus. And so anything I can do to stabilize those two intermediates will lower the energy of the transition state and increase the rate. Yeah, Caroline.
Yeah, sorry, what kind of solvent is acetone?
Polar, aprotic.
Okay.
Yeah,
Okay.
aprotic is the key here. Yeah, you don't have any H's that can serve as hydrogen bond donors. Okay. And so then the final thing is just like SN2 comes with its partner E2, the SN1 comes with an elimination pathway that we refer to as an E1 pathway. So Okay, so E1 stands for elimination unimolecular, and it's going to be competing with the SN1. Okay, the good news here is that the trends, if you go back to your notes and you think about the trends that favor E2 at the expense of SN2 or vice versa, they're the same here. Okay, and so for the SN1 reaction, I form that carbocation. Okay. And to complete the SN1, my solvent, which is also my nucleophile, needs to get to the carbon. So, oops. Okay. And so, so you can consider, what's going to favor attack at carbon. It's going to parallel what we saw with the SN2. So you want a small solvent / nucleophile. So like methanol would give you more SN1. Okay. If you start to bulk up the solvent or nucleophile, say we did it with T-butanol, you'd see more of the E1 elimination. So let me just back up and generalize this a little bit. So we'll call this R prime OH, and then I'll draw the other pathway, E1. And so then we basically have okay. And so as R prime, the group on the solvent gets bigger, it's going to be less efficient at getting at the carbon center and the carbocation, and so it's still going to start to do an elimination. So okay. And the other thing is the branching effect that we talked about. So, usually for these unimolecular ionizations, you're going to have a tertiary substrate. And so we're really just talking about beta branching. And so as we start to beta branch, it's going to get more hindered at carbon. The rate of attack at carbon is going to decrease, and you're going to start to see more elimination. So okay. So, there is a generalization to be made here, which is that, small reagents are generally going to favor attack at carbon for both SN1, SN2. Okay. And as things get bigger, either the substrate or the nucleophile, the elimination pathways are going to become more significant. Okay. So that is the end of the new material. And so what I want to do is spend the last 15 minutes doing a little bit of a summary from a different perspective, which I think might be helpful for you. But I'll first open it up to any questions that you guys have. All right. If there's no questions, I'm going to try and I want to go through something that I think will be helpful, and hopefully, those of you that are really enjoying this, which I assume to be each and every one of you, will appreciate this. So if you look at table 9.7 in the text, it goes through the factors summarizing SN2, E2, SN1, E1. And I want to sort of give you a different kind of short graphical summary. And the key point here is that SN1 and SN2 are actually limiting cases on a mechanistic continuum. They're the poles of that continuum. And the fact of the matter is most reactions are going to fall somewhere in between. And so, and again, in the context of an examination, we're not going to ask you where on the continuum a reaction may lie. We're going to consider reactions as being either SN1 or SN2, E2. But I think this is useful for bringing it all together. And so, okay, so we're going to talk about this. And, you know, at the very sort of end of this spectrum, we have a purely SN1 type of pathway. Okay. And so that involves two steps. In the transition state, for the first step, I'm ionizing my substrate. And so I basically have R with X, my leaving group. And the X is delta minus, the R is delta plus, okay? And then that proceeds to fully ionize and give me R plus and X minus, okay? And then in the second step, the nucleophile traps that carbocation. And so we have NU attacking the R group, and this is delta minus, this is delta plus, and then that goes on to products, okay? And so we call this the limiting SN1. So this reaction is sort of pure, unadulterated SN1, proceeds by ionization. You have no covalent bond formation. Between the substrate and the nucleophile. In the rate determining step. So it's unimolecular. The nucleophile is not involved at all in the rate determining step. You generate a free dissociated carbocation. Okay, and the reaction is first order. And if I have a chiral substrate, chiral non-racemic substrate, I get racemic products. So this would be 100% racemization. Okay. And then we can go and we'll start at the other end of this spectrum with the limiting SN2 case. Okay. And so in that scenario, you've basically got a single transition state, right? And we know that in that transition state, we've got partial bond breaking between the substrate and the leaving group and partial bond forming to the nucleophile. So we can draw that up here. Oops. Okay. And the bond forming, bond breaking is synchronous. Okay. And so okay, so it's synchronous with the bond breaking. All right. There is in the SN2, of course, there is no discrete carbocation. Your substrate proceeds through a single transition state. There are no intermediates. So okay. Because you have a single transition state, that is by definition the rate determining step. And so this is, and the nucleophile is involved, and so it's second order. And if you have a chiral non-racemic starting material, it proceeds very faithfully to the inverted product. So okay. So these are the two, the two things that we've been discussing. We just haven't said that they're limiting cases, right? And what's interesting is that what makes organic chemistry really interesting is that there's lots of intermediate cases, and there are sort of two intermediate cases that are often discussed. And the first one is what we call an uncoupled mechanism, and so this is more SN1 like. And so if we draw a reaction coordinate, it looks something like this. So this is uncoupled. Okay. And it's very similar to an SN1. So like the SN1, you've got a lot of bond breaking in that first transition state. So you have R plus, X minus. Okay. And that proceeds then to form a carbocation, but the lifetime of that carbocation is very short. Okay. And the way that we can express a short lifetime, on a potential energy surface is to have a low saddle point, a low point, which is this point over here. Okay. And so here you have the nucleophile trapping R plus. Okay. But the barrier for that trapping is very low. The cation is very high in energy, and it doesn't have time to freely dissociate from the leaving group. Okay. So okay. And so this reaction is still going to be first order in substrate. It's still kinetically going to appear to be a SN1 process because the nucleophile is still not involved in that first step. You're still getting to basically R plus, X minus, okay? But they aren't hanging around very long, okay? They're what we call a solvent separated ion pair. And the way we abbreviate that is just with a couple lines to sort of indicate that they're discrete intermediates. There's no bond, but they're not going anywhere. They're not going to have time to get away from each other, okay? So and the key with this is that because the lifetime is shorter, you actually start to see more inversion of some inversion of stereochemistry. So you don't get pure racemization, you get some inversion. And then the final case is what we call a coupled mechanism. And this looks more like the SN2. And it's where you go through a single transition state, but the nature of that transition state is a little bit different. And so you have essentially you have the nucleophile and the leaving group interacting in the transition state. And so this is second order, okay? But you have a lot more bond breaking than you do in a purely SN2 type of pathway. And I admit this doesn't do a great job of showing that. What I've tried to do is put the R as delta plus in the coupled mechanism, where it's delta minus in the purely SN2 mechanism. So it's really, that bond with the leaving group is really stretching and very far broken, but it's not fully broken, okay? And so there's no discrete carbocation, but RX bond, I'll just say largely broken in the transition state, okay? And then it's second order, and then you're going to get sort of more inversion in this pathway. Okay, so we can basically, say that as we move from left to right, the inversion increases. And as we move from right to left, the degree of cationic character increases, okay? And so the reason I go into this, again, you don't really need to know this, for this class, but I think it's useful because it hopefully provides some insights into why, this chapter has been so qualitative, right? Good nucleophile, bad nucleophile, good substrate, it's because as you start to change these individual parameters, you actually change the mechanism a little bit. It's not binary. These things aren't binary in terms of how they react, okay? And so, for example, right, as I am increasing, if I go hold every other variable constant, but say go from a methyl to a tertiary halide, right? What I'm doing is essentially moving from right to left along this continuum. As I get to the tertiary, I'm much more SN1-like, okay? It's sort of the reverse for a nucleophile. As I go from a weak to a strong nucleophile, assuming I can do an SN1 type of pathway, I'm moving from left, to right in the continuum. So the two processes are related by the degree of bond breaking and bond forming in the transition state. And as you get more bond breaking with less bond forming, you get more SN1-like. As those get more equal, you get more SN2-like. So I bring this up to put your minds at ease in the sense that hopefully you can see now why this is a very, qualitative discussion. Don't worry about memorizing the details on this slide, but just get the idea that, we're sort of pushing the system in one way or another by changing the parameters. It's not, all or nothing, okay? All right, so I'll end it there. I'm going to sign off, and then I'll be back at 10:25 if anyone wants to come to office hours. Otherwise, enjoy the break day, enjoy the weekend, and I'll see you on Monday. Monday, we'll do a giant recap of this chapter, okay? All right, take care.
Thank you.
Thank you.